And so on to our final topic, which is about total internal reflection. It's different to normal reflection that you'd get in a mirror. And their use in optical fibres, and it's the final couple of topics of this unit. So when you get light refracted as it passes from one medium to another medium, what happens, and you can see here, okay, it gets bent in this case away from this normal line. Okay, so this must be more dense, and this will be less dense. What happens is you also get a bit of light reflected, yeah, and reflected light is always at the same angle as the angle of incidence. This is the angle of reflection, the angle of incidence. Okay, this would be the angle of refraction. Okay, so total internal reflection is when all of the light, okay, is reflected back inside, in this case, the glass. Okay, so none is refracted. Okay, and it happens above something called the critical angle. Okay, so if it's below the critical angle, you get the situation that happened before, where some of the light is reflected but most is refracted. At the critical angle, okay, and this is the angle we're looking at between the normal and what we'll call the incident ray. At the critical angle, it runs along what we'll call the boundary. Okay. And again, some is reflected. And in our next example, it is above the critical angle, and then we get total internal reflection. Okay, so you can see it comes in and it goes straight back, so above the critical angle. You can see that angle is bigger, that might be, I don't know, 50 degrees now, okay, and it would be reflected back at the same angle. And you're probably thinking, well, what's the point in that, okay? But it is really important, as we'll see in a bit. So it only occurs, this total internal reflection, TIR, only occurs when the angle of light is above the critical angle, okay, and the light is travelling in the more dense of the two materials. So if it was trying to go from a more dense to a less dense, okay, from an optically dense material to an optically less dense material. So for example, from glass to the air outside the glass. Okay, and the higher the refractive index, okay, and if you remember, the refractive index is a measure by how much it refracts light, and the higher the refractive index, the more it refracts light, the lower the critical angle. Okay, so you can modify what that critical angle will be. And again, there's a lovely formula we've got to know, and this time it is refractive index equals 1 divided by sine of the critical angle. Okay, so let's say you've got a critical angle of a glass block that's 42 degrees, nice easy sum, okay. Calculate the refractive index, you do 1 divided by sine of 42, and you get 1.49, so pretty much the refractive index of glass, which, if you remember from earlier, is 1.5. Okay. If you want to calculate the critical angle of materials with refractive indices, so you don't have the critical angle, so it would be 1 divided by sine c. You'd have to do some rearrangements. So in this case, you would move the sine c up times 1.4 equals 1. Then you would divide by 1.4, so it'd be 1 over 1.4. Then you would need to do work that out. Okay, so sine of c equals 1 divided by 1.4, which is 0.714. Okay, and then to get c on its own, we'll have to inverse sine 0.714. And that equals 45.56. And because it's an angle, make sure you give it a degree sign. Okay, and the main use for this, or the main one that you need to know about, is in optical fibres. Now they're commonly used in broadband, and we'll have a think about the medical physics in a moment. So light comes in, okay, and instead of just leaving the optical fibre by refraction, okay, it is totally internally reflected, and that keeps on happening. It is always above the critical angle. Okay, so it keeps on going like that, and that means you can send things like broadband signals a long distance, which are, and they're like pulses of laser light. The main use you've got to know of is the use in endoscopes. Okay, so endoscopes, like this doctor here, placed inside the body. It's kind of got at the end, it's got a light to illuminate the area that the doctor's looking at, and also a camera, and then the camera transmits the signals back along, and even if it's curved, if it's having to go through somewhere strange, you can probably imagine where endoscopes are used, then it will keep on bouncing back, and the doctor gets an image like on here. So you can see exactly what's going on, even though that is inside the body. So it's pretty much looking at what's going on without being invasive. So it's a relatively non-invasive form of surgery, most commonly used to kind of like maybe stick down your mouth and have a look at what is going on in, say, your stomach, okay, or even further along. The final thing is just a very quick thing about lasers that you do have to know for the exam. Okay, lasers produce a very narrow beam of light that does not spread out. So whereas usually, let's say if you've got a light bulb, that's a terrible drawing of a light bulb. Let's say if you've got a light bulb, okay, light spreads out from that source. Okay, lasers do not do that. Lasers just produce a very thin beam of light. And the uses, they can cut through metal sheets if it's high powered enough, burn through or etch materials, and the minimum we've got to know about is cauterizing. Okay, so if there's say an area that needs cauterizing, which means kind of like brought together by heat, then you'd use it, and that would be used in, for example, laser eye surgery. Maybe I know, removing a bit of the cornea without covering by cauterizing. Okay, and there you go, used to reshape the cornea of the eye.